thank you very much, first of all, for Anil for inviting me, and for all of you for coming here. I'm really glad that there are so many of you here, and I'll try and make this a fun talk. Also I'd like to keep it informal, so if you have questions and so on, and you feel you really need to interrupt, please go ahead and do that, and we can try and make it more interactive if we do that. So I'm going to talk to you today about black holes and the reversibility of time. And my idea in the end of this lecture, at least, or my idea in this lecture, is to try and give you a sense of some of the theoretical puzzles around black holes and quantum mechanics, which really are a cornerstone of which really present some of the most significant difficulties in theoretical physics in constructing a theory of quantum gravity. So that's what I'd like to end up at, but in fact, since this is supposed to be a largely popular lecture, I thought I'll start with something that all of us know, which is the Newton's law of gravity. Okay, so in the end I'm going to talk about gravity, and I'm going to talk about many aspects of gravity, but I thought it's very useful just to start with what we first learned about gravity. And that is this very famous Newton's law, which all of us have studied a lot, and which tells us, and which was earlier discovered by looking at the motion of planets, and which tells us that if you look at the sun and you look at the earth, then the force between them is proportional to the product of their masses and inversely proportional to the square of the distance between them. And this is something that we've known now for more than 350 years. And there are several remarkable things about this law. One of the things that's remarkable is that this law is actually valid at so many scales. It's such an accurate description of nature. So in particular, this same law, you might have thought it was discovered by looking at planetary orbits, but really the same law is also the law that applies on Earth. And if we are looking at rockets and we are trying to send rockets up, then this is the law that we need to use to very great accuracy. The same law which was discovered by looking at planets is also what describes the motion of the moon around the Earth, right? So there's something which is very remarkable about Newton's law. It's still, and it stood us in good stead for 350 years now. But at some point, about 100 years ago, or a little more than 100 years ago, people realized that there was something else. Even though it was a very accurate principle of nature, Newton's law, people realized that there was something slightly unusual about Newton's law. And what was unusual about Newton's law was the following thing. You see, imagine that we have the sun and the earth, and then some huge giant, or say extraterrestrial giant, comes in and tries to push the sun a little bit. Okay, so moves the sun for some reason. So this is meant for comic relief, but you could imagine some natural forces or some natural events that cause the sun to be displaced from its position. So the question is, when does the Earth know that the sun has moved from its original position? Okay? Now, you might have thought that if you just followed Newton's law, Newton's law tells you that the force between the earth and the sun is proportional to the square of the instantaneous distance between them, and therefore if a giant were to move the sun, then the instantaneous distance between the earth and the sun would change. So therefore, if you were to believe in Newton's law exactly, then it would tell you that the earth would know that the sun has moved immediately, right? Instantaneously, the earth would know that the sun has moved. Now, we don't have to really do this experiment. This is just a theoretical question about an aspect of Newton's law. And this is the statement that Newton's law doesn't really respect locality, because you do something here, and even though there is something that you do here and the earth is separated by 8 light minutes from the sun, the effects of the gravitational force in Newton's law propagate instantaneously from the earth to the sun, or from the sun to the earth. Okay. Now, about 100 years ago, people realized that this was actually in contradiction with another very fundamental principle of nature, which was the fact that information cannot travel faster than the speed of light. Okay. So this aspect of Newton's law, which is the statement that the force between two objects is proportional to the inverse square of the instantaneous distance between them, is in contradiction with something else. It's in contradiction with the principle of relativity. Okay. So this is the fundamental principle in the theory of special relativity, and it tells you that the speed of light is an upper bound to how fast you can transmit information. Okay. And the theory of special relativity was discovered by many people, most often Einstein, but in fact a lot of the work had been done earlier by Lorentz and Poincaré in understanding this principle of nature. And you see clearly that the principle of relativity is in contradiction with Newton's law of gravitation. And so partly motivated by this, and partly by other theoretical considerations, people tried, set out to try and find a better law of gravity that would be consistent with this principle of nature, which we verified to very great accuracy and we believe is a true principle of nature. Okay? And so people came up with what's called the theory of general relativity. Okay? Now the theory of general relativity, if you look at it in detail, actually doesn't lead to predictions that are quantitatively very distinct from Newton's law. The theory of general relativity is something that to a very good approximation reduces to Newton's law, which it has to, because as I said at the beginning, Newton's law is something that we have verified to a very good approximation. But the philosophy of general relativity is completely different from the philosophy of Newton's law of gravitation. So the way people think about gravity now, and this is still the modern theory of gravity that we use to describe gravity today, is not in terms of a force between the sun and the earth. Okay? Rather, people invented an object where they said, well, really you should think of a fabric of space-time, and that fabric of space-time contains both the sun and it contains the earth. And what happens is that because the sun is a massive object, it causes some bends in this fabric of space-time. So it warps this fabric of space-time in a specific way, and the earth goes around the sun not because the earth feels a force that attracts it towards the sun, but because these orbits that the earth takes just happen to be the geodesics in this warped fabric of space-time. So they are the natural trajectories to take in this warped fabric of space-time. Okay. So what I want to emphasize to you, and what I'd like all of you to get from here, is that the language of general relativity, the philosophy of general relativity, okay, is very, very different from the philosophy of Newtonian gravity. We don't speak in terms of forces. Rather, we speak in terms of this fabric of space-time which mediates the force of gravity. And of course, the theory of general relativity is not just words of the kind that I said. There are some equations that go along with the theory of general relativity. Those equations were developed by Hilbert and then by Einstein. And those equations, this is the precise form of the equations that describe both everything I said in words in the previous couple of minutes, which tell you that the sun bends the fabric of space-time and then the earth moves in natural trajectories in this bent space-time. But there is a slogan that goes along with this, which is really the slogan that you need to remember when you think about general relativity. And the slogan is that matter tells space-time how to curve. Okay? And space-time, the curvature of space-time, tells matter how to move. So when you put together, and that's the second equation, and the first equation is matter telling space-time how to curve. Okay, so T mu nu is something that basically encapsulates the mass and the momentum of matter, the energy and the momentum of matter, and G mu nu is something that encapsulates some properties of the space-time. Okay? And so if you think of these two principles together, they allow you to use the matter content that of the sun to predict how the earth will go around the sun. Okay. So you have a very different philosophy, and as I said at the beginning, it's this theory in its quantitative predictions is different from Newton's law only in a very delicate manner. It required very accurate observations of the shift in the perihelion of Mercury and many very delicate observations to really verify that general relativity was giving us a more accurate description of nature than Newtonian gravitation. But the principle, the philosophy is very different. And of course, this answers the original question that we had, which is, what if a giant were to move the sun? So in the theory of general relativity, the language that we would now use is that if a giant were to come and were to move the sun, then this movement of the sun would create ripples in this fabric of space-time. So you see these ripples in this fabric of space-time, and these ripples in the fabric of space-time would propagate at a finite speed, which is the speed of light, and it would take 8 minutes for these ripples in the fabric of space-time to reach the earth, and therefore it is only after 8 minutes that the earth would know that the sun had moved. Okay? So this is how it answers the original question that we had about non-locality in Newton's law. Okay, so far, this is something that probably many of you have heard in one form or the other. But then people realized, by thinking more about general relativity, that the theory of general relativity led to some other predictions which were very different from Newton's law in some regimes. So in particular, when general relativity, after general relativity was formulated, very soon after that, this person, Carl Schwarzschild, found an exact solution to the equations of motion, to the equation that I showed you, and that exact solution gives you some kind of metric on space-time. So once again, this equation is not important. What this equation is roughly telling you is that if you take two objects in this metric of space-time, which are separated by some distance r in radial coordinates, so this is just the polar coordinate description of space-time, and some distance t in time and some angle theta and phi in the sphere, then the distance between them, which would usually have been this formula with m equal to 0 in the usual flat space-time that we are used to, is now given by this formula. And in fact, this space-time exactly solves the equations of motion of general relativity. Okay? So this is an exact solution to the equations of motion of general relativity. And if you think about this solution, you find that it has some very unusual properties. Okay? In particular, this solution that I just showed you is what is called a black hole solution. Okay? It's called a Schwarzschild black hole. And this solution describes not some nice regular mass like the sun sitting and bending space-time, but rather, if you think about the solution carefully, this solution describes something that's more like a tear or a rent in this fabric of space-time. Okay? So there's some kind of tear in this fabric of space-time, and that in these coordinates I described happens at this point which is at r equal to 0. Okay? But more interestingly, if you think about the solution, there is this region in this solution which is given by this radius, which is called the radius of the event horizon, and that's this black region that's pictured here. And this region has the property that once an object enters this region, there is no way for the object to go back to this ordinary red space that's sitting around. Okay? So this is the way you should think about the simplest black hole solution, which is the Schwarzschild black hole solution. There's something very bad happening at r equal to 0. There's a singularity. This is called the singularity at r equal to 0. And if you go very far away from where the matter is, then things look a lot like flat space, like the space we are used to. And then in the middle, there's this region which is called the event horizon, which is a region of no return, okay, which is a region after which once a body enters, it can never return back to ordinary space. Okay. Now, when this solution was first discovered, people realized that it had these properties, but they thought, maybe this is just some artifact of the kind of matter distribution we put in. And when you really think about realistic distributions of matter, these solutions will not really occur in nature. But of course, now we know that that's not true, and in fact we have a lot of astrophysical evidence of black holes. Okay? So in particular, if it turns out that if you look around at the universe around you, the universe is actually full of black holes. It's populated by black holes all over the place. For example, this is a black hole that lives at the center of our own galaxy. It's called Sagittarius A star, and it's a black hole which is very massive. It's a black hole that's 4 million times as massive as the sun, and it's about 26,000 light years away from us, and it's sitting at the center of our galaxy. Okay? So there are other black holes we've observed. For example, this is a picture taken by the Hubble Space Telescope. This is of a supermassive black hole that's even bigger than Sagittarius A star. That's about 500 million times as massive as the sun, and that's in a faraway galaxy that's 100 million light years away. So these are real astrophysical black holes that we have observed in the universe around us. Now, you shouldn't think that all black holes are necessarily millions of times more massive than the sun. This is an example of a black hole in our own galaxy. It's sitting this square inside here, and this black hole was actually studied and analyzed at the same time that I was a PhD student. It was, there were some of my friends who were involved in understanding this black hole. This black hole is, only a few times more massive than the sun. It's about 14 times as massive as the sun, and it's a very interesting black hole. It's a very interesting black hole because this black hole actually has the property that it's spinning about its own axis. And it's spinning so fast about its own axis that the event horizon of this black hole, this region, is moving almost to the speed of light. So it's spinning about almost 98% as fast as it can possibly spin, subject to physical limitations. So there's some very interesting black hole. This is a very interesting black hole that we've observed. And the main point I want to make by showing you these pictures is that black holes really come in all shapes and sizes, from being millions of times or billions of times, sometimes as massive as the sun, to being just a few times more massive as the sun, to black holes that are just sitting there, they're just very fat and sit there and don't move, to black holes that spin around as fast as they possibly can. Okay, so there's really a wealth of very interesting astrophysical phenomena that we've seen and we've observed about black holes. Okay. In particular, one of the other interesting astrophysical phenomena, that we've observed very recently in the past few years has been the emission of gravitational waves from the collision of black holes. So, if black holes collide, they emit gravitational waves, and earlier, all of these were pictures that were taken in various electromagnetic spectra, but now we also have the ability, by using these huge gravitational wave detectors, to detect the emission of gravitational waves, and that has further served to verify what we thought we understood about black holes. So we've really, there's really a lot of interesting astrophysics about black holes, and as Anil pointed out, this is a very active field that continues, to advance very rapidly nowadays. Now, in fact, as I said, there's a lot of very interesting astrophysics about black holes, but for the remainder of this talk, I don't really want to talk about the astrophysics of black holes, even though that's a very interesting subject in itself, but that's not what I work on. And in fact, the kinds of things that I work on are more to do with very, simple black holes, but which nevertheless lead to very, very fundamental theoretical problems. And so I'll try and describe now the kinds of things that we think about, and how even if you don't think of all of these exciting black holes which have all these accretion disks and emit a lot of waves and gravitational waves and electromagnetic waves, there are still a lot of very interesting questions about black holes that can occupy theoretical physicists. Okay? So the kinds of black holes that people like me or string theorists think about are very simple black holes. They're what you might call vanilla black holes. So, you've probably heard the joke, I'm sure all of you have heard the joke that, if you go and you talk to physicists, they will say, let's consider a spherical cow. Okay? So these are the spherical cows of black holes. These are black holes where you have a star, and the star has lived and it has emitted a lot of light, but at some point the star dies, because it runs out of fuel, and because it's a big fat massive star, it collapses under its own weight, and eventually it collapses past this dashed line, which is where the event horizon of the star would have been. And then once it has gone past the event horizon, nothing in the universe can stop it from collapsing some more, and so it collapses even more till it just becomes a singularity, and the late stage of this collapse is a Schwarzschild solution that I showed you. Okay? So this is a very simple universe. The universe basically consists of this star which is going to collapse and form a black hole. Okay? And it's a spherical black hole, and there's no other matter around. So in particular, you wouldn't, if you really had this black hole, you wouldn't be able to take all these fantastic astrophysical pictures that I showed you about. Nevertheless, even this very simple spherical cow process leads to very, very deep questions about quantum gravity, as I'll now describe. Okay? So before I do that, let me just try and say that, in the rest of this talk, it's of course very inconvenient to keep drawing these kinds of cartoons where, you show what happened to the star at one point, and then you say what happened to a star a little later, and then you say what happened to a star a little later. And so it's often convenient to put these things in what's called a space-time, in what's called a space-time diagram. And so you'll often see diagrams of this kind in the remainder of the talk. And in these diagrams, time goes up on the y-axis. So I'm sure some of you have seen these diagrams before. And you have radius on the x-axis, and you have time going up on the y-axis. So this is the same picture as what I showed you previously, which is a picture which says that here was a star, and then as time went up, the star collapsed, and then it formed this singularity. And so in the beginning, there was no event horizon, and at some point the event horizon forms, and now you have this event horizon at late times as you go up in the picture. In fact, this is also not the most convenient way to think about black holes. And the reason it's not the most convenient way to think about black holes and collapse is because, it's not very clear why this purple line is an event horizon. It looks like just some radius r, and it's not clear why it's the event horizon. Why is it that when something crosses it, it can't return outside to normal space? So in fact, there's an even more convenient way to draw these space-time diagrams, and that is to make a change of coordinates so that light rays go at 45 degrees in your coordinates. And when you do that, you come up with what's called a Penrose diagram. So this is you shouldn't get worried about all this. This is the same picture as the cartoon I showed you previously, plotted on a space-time diagram with something done to the coordinates, with the coordinates stretched and scaled in such a way that light rays go at 45 degrees. So now you see that the event horizon is itself a light ray. And this gives you a clear reason why once something crosses the event horizon of a black hole, it can never escape again. And the reason is that the event horizon is itself a light ray. And once a light ray crosses you, you can never catch up with a light ray. Okay. So this is something that we know already from special relativity, that if there's a light ray which is coming to hit you, if you run really fast and almost at the speed of light, you can stay ahead of the light ray if you keep accelerating. But once a light ray has crossed you, there's no way to go and catch up with it and say, wait, I want to talk to you. You can't do that after the light ray has crossed you. Okay? So the event horizon is an event horizon because it is a light ray in space-time. Okay? So once an object crosses this, there's no way for the object to return to space, because the event horizon is describing basically the trajectory of light. Okay? And therefore, the reason it's convenient to draw pictures of this kind is because they make what's called the causal structure of black holes clear. Okay? So this is the way you'll often see people talk about the causal structure of black holes in coordinates and pictures of this kind. Okay? Okay. Now, so I said, we have a spherical cow, but now apart from a spherical cow, we'll start, poking the spherical cow a little bit. And this is again something that you can do theoretically just using what you understand. And so, we understand a fair amount about black holes and the collapse that I showed you previously. But now you can start asking the following question. You can start asking the question, you can say, well, you took this black hole which formed from the collapse of a star, and then you waited for some time, and then after you waited for a long time and you've allowed the black hole to settle down, this mischievous giant who was pushing the sun around now comes again with a star in his hand, and he pushes the star into this black hole. Okay? So what happens? Now, of course, we can't do this experiment because we don't know of any mischievous giants of this kind. But we can at least theoretically try and calculate what would happen if you took a black hole and you threw in some additional matter. So the equations of general relativity give us a well-defined framework to try and analyze the results of processes of this kind. Okay? So this is a picture of the same process drawn in terms of Penrose diagrams. You had this black hole which formed from a star. The star collapsed. It formed a black hole. It forms a singularity. And at some point, someone throws in some additional matter. That's this orange line. The orange line goes and hits the singularity. And of course, once the orange line crosses the event horizon, it has become part of the black hole. And so the black hole grows a little bit. It eats up whatever matter was part of the orange line, and it grows a little bit. Okay? So that's a qualitative description of what happens. But in fact, in the 70s, physicists analyzed this in some detail, and they found something very interesting. They found that if you analyzed in detail how the black hole responds, you could describe the response of the black hole to perturbations of this kind by using the following equations, which you have seen. Okay? They found that the response of black hole to perturbations of this kind was described by equations that were exactly the same as the equations of thermodynamics. Okay? So they found that if you threw in some matter, which was dm, so some very small amount of matter dm, then as I said previously, the horizon would grow. It would grow by this amount dA, and there was a constant of proportionality, which is what's called the surface gravity of the black hole, and that always appeared in front of this coefficient. Okay? And this is very similar to the first law of thermodynamics, which tells you that if you throw in some energy, which is like mass, then the change in the energy can be related to some other quantity in this manner. Now you might have said, why does it look like the first law of thermodynamics? And the real reason is, of course, that there's also a second law of black hole dynamics that tells you that black holes, the area of black holes in any such process you can imagine classically, always grows. It never reduces, which is a lot like the second law of thermodynamics that tells you that if you have some system, you can only increase its entropy, you cannot decrease its entropy. Okay? So people found that the response of black holes to perturbations to quasi-static processes, where you took a black hole, you allowed it to collapse, and then you threw in some matter, was a lot like the response of gases or ordinary thermodynamic systems to the same kinds of quasi-static processes, where you take a system, you allow it to settle down to thermal equilibrium, then you probe it or you poke it, you insert some energy, and you observe how the system responds. And people found that the equations that describe thermodynamic objects were very similar to the equations that describe black holes. Okay? So in a sense, these very remarkable astrophysical black holes that I showed you pictures of are described by laws that are very similar to the laws that govern thermodynamics, okay, that govern your cup of tea or that govern this bottle of water or so on. Okay, so this was a very remarkable discovery that people made, and the thing that went into this discovery was just a careful analysis of the equations of general relativity and the equations that describe black holes. Okay? I should also say one more thing maybe about the second law of thermodynamics. The reason the area is special is because you can imagine processes in which sometimes the mass of the black hole goes down. It's not true that the mass of a black hole always increases. In fact, if you think of these spinning black holes, like this black hole I showed you at the beginning, which was spinning almost at the speed of light, you can imagine doing processes to it which will extract mass from the black hole, but you can never imagine a process that will reduce the area of a black hole. Okay? So it's really the area of the black hole that functions like the entropy. Okay, so now people discovered this in the 70s. There were many people, Israel and Bekenstein and many others who worked on this and who discovered this. But for a while, people thought that, well, so what? After all, there's a lecture in the Feynman lectures in physics that perhaps some of you have read, which is specially devoted to pointing out that the same equations have the same solutions. Okay? So maybe some of you have seen this lecture or have read this lecture in the Feynman lectures in physics. And that tells you that often in physics it so happens that the same equations show up in very different places. If you think of a mass on a spring is described by the same equations that describe an LC circuit. Right? And so when you want to solve an LC circuit, if you know how to solve a mass on a spring, you can also solve an LC circuit and vice versa. But that doesn't mean that an LC circuit is a mass on a spring. These are different physical objects. It just so happens that they're described by the same equations. So what I pointed out here is that the dynamics of black holes and quasi-static processes is described by the same equations that describe thermodynamics. But you might have said, okay, so what? That doesn't mean that black holes are really thermodynamic objects. It doesn't mean you should really talk about the area as an entropy or the surface gravity as a temperature. But one of the main discoveries that was made around the same time, it was made by Hawking, and in fact this is what Hawking is most famous for, was that in fact the analogy between black holes and the laws of thermodynamics is not a formal analogy. It's not just a case of the same equations having the same solutions, but there is something real and physical about this analogy. And what Hawking found is that when you add quantum mechanics to the picture, if you think of quantum fields or quantum mechanics are in the neighborhood of black holes, then black holes really develop a physical temperature. And that physical temperature is proportional to 1 over the inverse mass, and it turns out to be proportional also to the surface gravity of these black holes that I described previously. Okay? So this was Hawking's famous discovery that black holes really have a temperature, and what it means to really have a temperature is that they radiate the same way as a body with a certain temperature would radiate. Okay? And I won't try and describe in detail why this happened, but here's a very quick physical reason why quantum mechanics leads to black holes having a temperature. You see, you think of this black hole here. Now in quantum mechanics, space-time fluctuates. Everything in all the fields in space-time fluctuate, and these fluctuations, which occur even in the vacuum, lead to the production of pairs of particles and antiparticles near the event horizon or just across the event horizon. Now what happens is that the partner which is outside the event horizon can stream off to infinity, while the partner which is inside the event horizon falls into the black hole. So it looks, if you're sitting at infinity, that there is a steady stream of particles that's coming out, which is really caused by vacuum fluctuations happening in the neighborhood of the event horizon of the black hole. Okay? So this is of course not a very precise explanation, but it really does capture the essential physics of what leads to Hawking radiation. And as a result, if you're an observer who's sitting at infinity, who's sitting somewhere here, it looks like the black hole is emitting particles with a certain temperature, and that was the temperature that Hawking calculated. Okay, now, so the picture that comes about when you think of black holes in the presence of Hawking radiation is the following. It's that black holes are not really black objects. Classically, if you only thought of the theory of general relativity, you would get the picture I showed previously, where you had space-time and you had this black object that was just sitting in the middle. But in the presence of quantum effects and quantum mechanics, what happens is that you really have this black object, and this black object has a ring of you might call it quantum fire or quantum radiation that surrounds it, and this ring is a ring of Hawking radiation. Okay? So now the picture that you have of a black hole in the presence of quantum mechanics is that you have this tear in the fabric of space-time, and then above that you have some some weak quantum fire that has started that causes this tear in the fabric of space-time to radiate at a constant rate with a temperature that we can calculate precisely. Okay? Now, before I go forward, let me just try and give you a sense of some of the numbers that are involved. So the first thing to realize, I guess, is that because Hawking radiation is caused by these quantum effects, it's a very delicate effect for astrophysical black holes. In fact, for a black hole which had the mass of the sun, the temperature that you would get by looking at Hawking radiation would be 10 to the minus 8 Kelvin, which is a really, really small temperature. Okay? But of course, if you had a black hole that was much smaller, that would be much hotter. But if you think of these supermassive black holes that I showed you, they would be millions of times cooler than even this temperature. Okay, so Hawking radiation is something that's very difficult to detect astrophysically, okay? Because the black holes that we know are always big black holes that have masses of the sun. There's nothing that prevents the existence of smaller black holes, but we haven't observed them. Okay. Now, what is it that happens if you think about this a little bit more? Well, if you think about this temperature a little bit more, then you will realize that if you think of this spherical cow setup that I had, where you have this black hole which has formed, which is formed by the collapse of some star, then as a result of these quantum effects, this black hole develops a temperature, and even though it's a very small temperature, there is a finite temperature. And as I said, the main point of the black hole having a temperature was that the black hole starts radiating. And the radiation is given by the ordinary Stephen-Boltzmann law that all of us have studied. And it tells you that the rate of loss of energy is just sigma into T to the power 4, where T was this temperature I calculated, times the area of the black hole. Okay? And if you put in the formulas for T and the area and so on, you find that the black hole loses mass with a steady rate that's proportional to 1 over m square and some constant that comes about that depends on various fundamental constants of nature. Okay? So all black holes lose mass through Hawking radiation by a formula, and in a rate that's proportional to 1 over the square of the mass of the black hole. Okay? Now, what this means is the following. It means the following. It means that if you wait for long enough, if you take a black hole and you wait for really long, then the black hole will eventually lose all of its mass through this Hawking radiation. Okay? So a black hole is not only not black, not exactly black, it radiates, and this radiation has a physical consequence. It means that black holes have a finite lifetime. Okay? Now, this lifetime is a very long lifetime for astrophysical black holes. Okay? In fact, if you were to take the sun and make a black hole out of it, the lifetime of the sun would be 10 to the power 67 years, which is much, much longer than the age of the universe. So really, for astrophysical black holes, this finite lifetime doesn't mean anything. But as I said at the beginning, there's no principle that we know of in nature that prevents the formation of smaller black holes. And if you did have smaller black holes, then this lifetime would be a meaningful concept. And for example, the reason I take 400 tons, by the way, I should say, is the following. Sometimes when I give this talk, I get questions saying, is there a black hole at the center of the Bermuda Triangle? Okay, so let's say there was a black hole at the center of the Bermuda Triangle, and that black hole swallowed up a plane. Okay, so this 400 tons is roughly the mass of a fully loaded plane, a fully loaded passenger plane. If you took a fully loaded passenger plane and you threw it and you made a black hole out of a fully loaded passenger plane, in fact, this black hole wouldn't stay for very long. So even if there was a black hole at the center of the Bermuda Triangle, Hawking radiation would cause this black hole to evaporate and basically evaporate entirely in about 5 seconds. Okay, so this is actually even if there was a black hole at the center of the Bermuda Triangle, it doesn't exist anymore. But the important thing here is that if you can form smaller black holes, and as I said, there's no physical principle. It's really a technological obstruction as far as we understand to the formation of smaller black holes. For these smaller black holes, the lifetime would be much smaller. It would be something that would be comparable to mundane time scales that we're used to. Okay. Okay. So now, the fact that black holes have a lifetime, as I said, is something which is something we believe to be true of black holes. It's not something we can observe for astrophysical black holes, but it's something that we would be able to observe if we could do experiments by forming smaller black holes or by observing smaller black holes. Now, because black holes have a finite lifetime, you can imagine the following story you could write about a star. Okay? So once in this spherical cow universe of ours, there was a star, and the star lived in splendid isolation. It lived in the universe without anything around it. And at some point, the star grew old and the star died and its internal fires died. And then the star collapsed. to form a black hole, and when it collapsed to form a black hole, these quantum effects near the event horizon of the black hole forced it to give off radiation, and in the end this radiation caused the star to evaporate away completely and end up entirely in thermal radiation. Okay? So this is the kind of story you could write about this spherical cow universe of mine that I've been describing. Okay? Now if you think about this story a little bit more, you will see that there is something unusual about this story. There's something slightly, there's something slightly troubling about this story. Okay. The thing that's troubling about the story is the following. You can imagine forming the same kind of black hole with the same mass in two different ways. You could take one star, and that star would give rise to a black hole of one type. You could take another star, which was a very different star, which was made up of very different matter. Maybe one star had more hydrogen, maybe the other star had more helium, maybe one star had some kind of distribution of hydrogen and helium, maybe the other star had a different kind of distribution. So these are really distinct stars, and you could take these two stars and you could make black holes out of each of them. But at the end of the story that I described, both the black holes would end up in purely thermal radiation, and that radiation would only depend on the temperature of the black hole, and it would not depend on all this other information that was present in the stars to begin with. Okay? So this story that I described gives rise to the following kind of situation. It gives rise to a situation where you can start with two different initial states and end up with the same final state. Okay, so if you think of these arrows as representing time evolution, then this kind of process, if you've just followed it through, would suggest that you cannot in this situation reverse the time evolution arrows. Okay. Now this is something that's anathema to everything that we know about physics. Okay. In all examples where we've studied physics, it's always the case that you can always reverse the evolution of time. Okay. And this is true in all settings. In the beginning, when we learn in class 8th about ballistic propagation, and you learn if you throw a ball with some speed where it will land up, there's something else that's sometimes unstated, but that's always true, which is if you know where the ball fell and the velocity of the ball, you can also calculate where it came from. So if I tell you the position and the velocity of the ball at some point of time, you can not only predict the future, you can also retrodict the past. And this is something that's also true in quantum mechanics. It's also, in quantum mechanics, if you look at Schrödinger's equation, if you give me the wave function at one point of time, I can predict the future and I can also retrodict the past. So all the principles and all the theories of fundamental physics that we have so far have the property that time evolution can always be reversed. Okay? If you give me the state of the world at one point of time, I can tell you what it will be at some future point of time. I can also tell you where that state of the world came from. Okay? And the paradox here, the problem is that black holes look like they don't satisfy this fundamental principle of physics. Okay. So if you just think about black holes carefully and add to it the principles of quantum mechanics that we think are correct, and you use the principles of general relativity that we think are correct, that leads you to this internal inconsistency. It leads you to the situation which is in contradiction with something that you started with, which was Schrödinger's equation, which was really allowing you to predict this evolution. Okay. So there is an internal inconsistency in putting together the theory of quantum mechanics and gravity, and it is this. It is the fact that if you put these theories together, they seem to predict that you can start from different initial states and end up at the same final state. Okay? And this is what's called sometimes the information paradox, and it's one of the fundamental obstacles to constructing a good theory of quantum gravity. So now, here's the possible solution to this paradox, which is something that I think we understand if, that at least a fair amount of recent work has shown is possibly the case. And that's the following solution. You see, you might have thought that this is something that happens in other situations as well. You might have thought that, if I roll this bottle, in the end it will come to a stop, right? And once it's come to a stop, it looks like, I can't predict really where it came from. In the case of the bottle, we know that what's really happened is that the information that was present in the bottle in the first place has gone into the molecules of the table, and if you kept track of all the fundamental microscopic degrees of freedom, then you would have been able to predict what happened to the bottle, where the bottle came from. So even though things that we see as dissipation are really not dissipation, but are really correspond to the fact that information that's present in coarse-grained degrees of freedom goes off into fine-grained degrees of freedom. Okay? So, the solution to the information paradox that is at least most commonly believed is that it looks like you have a black hole and it emits this radiation, and indeed it's true that this is a computer generated picture, that if you took this black hole and you look at this set of dots, there are 4 colored dots here which you can think of as corresponding to different kinds of wavelengths of photons that are being emitted. So they are red, yellow, blue and purple photons, and indeed the photons were placed here in a completely random way. Okay? So you might have thought that the distribution of photons that's emerged is totally random, but in fact that's not true, because there is more information in the full distribution of photons than there is in just thinking of the marginal distributions of all the individual photons. In particular, in this picture, there is information in the form of correlations in the positions of the photons. So if you stare at this picture carefully, you will find that every time you have a purple dot, if you draw a line exactly diametrically opposite to that, there's a yellow dot, and every time you have a red dot, if you draw a line diametrically opposite to that, there's a blue dot. This is an example of what are called 2-point correlations. Looking at the position of every individual photon, that's completely random and the photons are distributed randomly, but there are 2-point correlations in the photons that store information, that store more information than is present in the individual photons themselves. Okay? And the claim is that very small delicate correlations of this kind between the different kinds of Hawking photons that are emitted are enough to preserve all the information that was present in the black hole in the first place. Okay? And in fact, you can estimate, and this is something that many of us have worked on in the past few years, it's something I have also worked on in the past few years, you can estimate how small these correlations have to be to preserve information, and it turns out that these correlations can be as small as exponential in the entropy of the black hole, which, if you remember what I was saying about 20 minutes back, is proportional to the area. And in particular, for a black hole which is as large as the sun, this entropy is 10 to the 70. Okay? So you could have really, really delicate correlations in the Hawking quanta that are emitted, and these really delicate correlations would be enough to store information about what formed the black hole in the first place. Okay? So the claimed resolution to the paradox is that really the calculation that you did wasn't precise enough to keep track of all of these really, really small correlations, and if you were to keep track of these really small correlations, then you would learn how to preserve information in Hawking radiation as well. Now, if that was the end of the story, that would be kind of a boring end of the story, right? What would be the point of telling you all the story if in the end the point was just to say, black holes behave like ordinary thermodynamic objects? Of course, there's a catch. Okay? The catch is that you can ask, even if you have these tiny correlations, where do these correlations come from? If you think of the process of Hawking radiation, it's the following kind of process. You have the star, and the star collapsed, and the star has collapsed and become really small, right? It's gone all the way down to the singularity. And if you remember, when I told you about the formation of Hawking radiation, I said that the Hawking radiation was coming from vacuum fluctuations near the horizon of the black hole. Right? So if you have these vacuum fluctuations which are coming from the horizon of the black hole, this is one pair that's going out and this is the pair that's falling in, then where do even these very, very tiny correlations that I said preserve the information come from? How do they affect the dynamics that's happening at the event horizon? Because the event horizon in a black hole, if you wait for long enough, is just empty space. The matter that formed the black hole is not present at the event horizon anymore. It's fallen in. Okay? So of course, you can say a little bit more. You can in fact argue that it's not that the information that's present in the black hole comes out all at the end. So this is a plot of actually how much, if you look at the negative of this, it will tell you how much information is present in the radiation that comes out, and you can argue that the information starts emerging after about half the black hole has evaporated. It's not that the information can sit in the black hole all the way till it's become really small and there's just some matter there and then the black hole evaporates, but really the information has to emerge while the black hole is still big and while it's still well described by physics as we understand it. Okay? So there's still a puzzle, which is to ask, even if you say that there are delicate correlations which can preserve information, how are these delicate correlations formed if Hawking radiation really emerges from the vacuum? And that leads to another interesting answer, and the interesting answer is that in fact, even though the matter is far away from the horizon, there have to be small non-local effects that transmit information from the matter to the horizon. Okay? So the only way you can preserve information in the evaporation of a black hole is actually by transmitting information non-locally from where the matter is to the event horizon, and that is the only way. It has to be a very small amount of non-locality. The non-locality is something that's a very delicate effect, but this delicate effect is something that's important and necessary to preserve a fundamental principle of quantum mechanics. Okay, so there are very delicate effects which are exponentially small in the entropy of the black hole, which are necessary to preserve this fundamental principle of quantum mechanics, which is that time evolution is reversible, and that forces you to give up the notion of exact locality in black holes. Okay? Now you might have asked, and I'm sure many of you are thinking, how do you know that something like this is true? So of course we don't know that, it's very hard to do experiments and try and observe something like this really, but in fact you can at least construct toy models where you can try and understand, at least in some well-controlled toy settings, that such an effect should be true. So in fact, if you think a little bit more about the effect that I mentioned, the precise statement of this effect is really the following. It's a statement that if you have this black hole which is evaporated and there's some degree of freedom that lives here, there's some matter or something else that lives near this blue dot, then by making a careful set of observations outside, even though these observations are spatially separated from where this blue dot is, you can actually recover the same degrees of freedom in this blue dot by thinking of degrees of freedom in this red dot. Okay, so there's a slogan that goes along with this. The slogan is that the degrees of freedom inside the black hole have to be scrambled versions of degrees of freedom that live outside the black hole. Okay? And this you see is quite in contradiction with the usual notions of locality. I say I have degrees of freedom that live in my left hand. They are completely distinct from the degrees of freedom that live in my right hand. Those of you who studied quantum field theory, this is the statement that operators here commute with operators here. They just exactly commute. But the statement is that in quantum gravity, if you need to preserve this fundamental principle of reversibility of time evolution, then you do need some notion of the fact that sometimes it might happen that degrees of freedom here are actually scrambled versions of degrees of freedom somewhere else. Okay? Now, why, as I said, why should we believe this? And the reason at least is that in some examples of quantum gravity that we think we understand well, you can in fact calculate and show that this has to be the case. So let me very briefly describe why something like this is plausible. I'm going to spend about 2 slides of technicalities. I've shown you a lot of pictures in this talk, but since this is a physics talk, I felt it's important to have at least some technical things. But don't get scared. I'll try and say it as simply as possible. And I'm going to spend a couple of slides trying to describe why such an effect has to be plausible. So the setup in which we can make such an effect plausible is actually what's called anti-de Sitter space. Okay? This is a toy model of gravity because this is an example of a universe which has anti-de Sitter space is a universe which has what's called a negative cosmological constant. So those of you who have an interest in cosmology know that our universe has a positive cosmological constant, but you could imagine a universe which has a negative cosmological constant, and that's what's called anti-de Sitter space. And what's special about this universe is that this universe looks like gravity in a box. Because you have this negative cosmological constant, things basically get confined to some finite region, and so it's simpler to understand gravity in this universe because it looks like gravity inside a box. Now in this example of anti-de Sitter space, you can actually prove that in quantum gravity it must be the case that the degrees of freedom that live in this point P can be written in terms of a scrambled version of degrees of freedom that live inside this red band B, which is an example of the non-locality I described. And the way this goes actually is not very complicated. So I thought I'll try and describe to you, at least I'll try and give you a gist of how you would prove a result of this kind. So the way you prove this result is as follows. Let's say there's some degree of freedom that lives at this point P. Okay? Those of you who studied quantum mechanics know that if you have every degree of freedom is described by some observable, some operator, and you can always take this operator and you can expand it out in some complete set of states. Okay? Then, this is just an expansion in a complete set of states. Then it's also true that in any whenever you have quantum fields, which includes gravity, that live in a space-time of this kind, if you're given the vacuum of the theory, you can always act on it with an operator in one place and create any state in the theory. This is sometimes the statement that if you're allowed to act with arbitrary operators in quantum mechanics that live inside this room, you can create the moon in the Andromeda galaxy. And this is a true fact about the world. This is not a violation of locality, because in fact you're never allowed to act with arbitrary operators. Okay, for those of you who studied quantum mechanics, you're only allowed to act with unitary operators. You're never allowed to act with arbitrary Hermitian operators in some region. But if you could create any state in the theory, and that's this second line. Then there is a third fact about gravity, which all of you are familiar with, which is very special to gravity, which is the fact that in gravity, if you want to measure the energy of something, you can measure the energy of something from a distance. Okay? How do we know that the sun has the mass that it does? It has a mass of 2 × 10⁻30 kg. None of us has been to the sun, but how do we know that the sun has the mass that it does, or that these black holes in the center of the galaxy have the mass that they do? The way we know that is by looking at the fall off of the gravitational field far away. So there is a special fact about gravity, which is that the energy of gravity, the Hamiltonian, is described by a boundary term. Okay? It's something that you can measure far away. You don't need to actually go and physically measure the energy of the object. You can actually just look at the fall off of the gravitational field far away. If that is the case, then there is a unique state which has zero energy, which is the vacuum, which you can get just by taking this operator and putting it inside a big exponential. And if you combine that with this statement, which is sometimes called the Riesz-Leiter theorem, you can see that you can actually reproduce this operator phi in terms of operators that live at a distance. Okay? So this is something that, at least in these simple models of quantum gravity, where you can verify all of these equations, is something that you can check. Okay? And it's something that one of the points of showing you this equation is to point out that it's not something that's very complicated to check. It's something that already, with a little knowledge of quantum field theory and quantum mechanics, you can check. Okay, so I don't want to go much more into details, but the fact that this happens is really a sign of something deeper in quantum gravity that we've learned, which is the fact that quantum gravity has dynamics that's holographic. It has dynamics that's holographic, which means that if you look at quantum gravity in some region of space, you can often describe what's happening inside that region of space by looking at the boundary of that region of space. All the information that's present inside the bulk of some quantum gravitational system is also present at the boundary of the quantum gravitational system. Okay, so in that sense, something that we've learned about quantum gravity is that quantum gravity is a system which is holographic. Okay, so just like a hologram, in a sense, the boundary contains information. And the thing that I pointed out that's interesting here is that this is something you can verify already using just some simple formulations of gravity and some simple statements about quantum field theory and gravity that we have already verified and know to be true. Okay. And this is something that's relevant for the information paradox, and it tells you that there is a way to form these correlations that are required to preserve information that's present, that was present in the star that collapsed to form the black hole. Okay, so you might have asked, is this effect true in our universe? I said that we can demonstrate the effect mathematically in certain toy settings, and so is this effect true in our universe? And if it would be true, and we don't know, of course, if it's true, we don't even know theoretically or mathematically if we expect such an effect to be true. If this effect would be true, it would be the following statement. It would be the statement that the information about some degrees of freedom or something that's happening inside here at some point can actually be obtained by a very large number of careful measurements on a big sphere that surrounds the point. Okay? So the statements I've been making so far would, if you translated them to our universe, correspond to a statement of this kind. Now we believe in some moral sense this should be true, but as I said, this is an open problem. We don't even understand mathematically, forget about actually trying to verify it in the real world, whether a statement of this kind would be true. But, so this is an open problem that I'll leave you with, but let me just conclude with some philosophical remarks. If such a statement is true, and at least as I said in some toy models of gravity we believe such a statement is true, then once again, the effects that correspond to such a statement are very delicate. Just like the effects that, as I said, the effects of general relativity are very delicate. But the philosophical picture of space-time that would emerge if such an effect would be true would be very different from this notion of a continuous fabric of space-time where there were different degrees of freedom living at every point in the space-time. Rather, maybe a more accurate way to think about the universe in the presence of such effects would be to think in terms of these threads of space-time, which would be the statement that if you had access to all these threads in some boundary, then you would know what was happening in the middle instantaneously. Okay? So in a sense, the number of degrees of freedom are not determined by the area, but rather determined by the perimeter of something here. Okay? So there's some finite information carrying capacity to space-time, and the way you can think about that is by thinking about these threads of space-time, which tells you that you don't really have independent degrees of freedom that live at every point, but rather there's some connection, and if you had access to all of these threads, then you would know what was happening instantaneously at the center of the space-time. Okay, you shouldn't think too much about this picture because it's not a picture that we can make very precise. It's a cartoon, but the interesting thing is that this gives you a sense of how, by thinking about these very delicate effects, you get this progression of very interesting and different perspectives on the nature of space-time. So I started this talk by talking about Newtonian gravity, and by saying that in Newtonian gravity we thought about the sun and the earth attracting each other with a force, and that was a completely non-local theory, right? Because the sun and the earth attracted each other with a force that was proportional to the instantaneous distance between them. And we said, wait, we don't like non-locality. We don't want theories that are non-local because they violate relativity. And so we said, well, so let's change the way we think about space-time. Let's instead invent this fabric of space-time, which gives rise to a local theory, where all effects propagate via ripples on this fabric. So the way an effect propagates from here to here is by ripples on this fabric, not by means of forces between these two objects. And then we thought a little bit more about this theory, and we said, well, this theory gives rise to black holes, and if you think of black holes in quantum mechanics, that gives rise to Hawking radiation, and that gives rise to certain paradoxes. And if you think about how these paradoxes have to be resolved, then maybe you have to give up this picture of a continuous fabric of space-time, and you end up with another different picture of space-time, which is in terms of these discrete threads of space-time. So this, is a very interesting, at least philosophically, very interesting question about the universe. And this last, even though I've drawn it as an arrow, is really something that deserves to be fleshed out more and understood better. So maybe some of you will help to understand that.